Welcome to the GARCH Volatility Forecast mini-tutorial. In this video, I will use NumXL to analyze, model, and forecast the volatility for the S&P 500 ETF SPDR. To start, I've downloaded the monthly closing prices for SPDR from January 3rd, 2000 to the present date. Let's start by computing the log returns for the SPDR ETF. We'll use the NumXL diff function with the logarithmic closing prices. Now select all the cells below. Hit F2 and press Ctrl-Shift-Enter. The monthly log returns are now copied in the new range. Now format the output range. Notice that the first cell shows NA, or not available. Let's plot the time series in a graph. First, select the input time series. Now select the returns cell range. Click the Insert tab. Using the line graph icon, select a 2D type of line graph. Move the graph to the right and reformat the graph. The monthly returns look centered over the x-axis, with no trend over time. Now let's examine the stationarity assumption of the time series. We'll compute the 12-month moving average and the exponential weighted volatility, or the EWMA. In the formula editor, type WMA. Select the monthly log returns as the input time series. Again, select all the cells below. Hit F2 and press Ctrl-Shift-Enter. All values are now copied to the new range. Reformat the output range into percentages. For the volatility, we'll use the NumXL EWMA function. First, type NA in the first cell. In the following cell, type the EWMA formula. Reference the returns up to the last observation, which in this case is H3. Now let's do the second cell. This time, fix the starting cell to H3. Accept the default values for the remaining parameters in the EWMA function. Now copy the formulas to all the cells in the column. Plot the WMA and the EWMA in the same graph as monthly log returns. Assign the EWMA to the right-hand side axis. Note that the 12-month moving average is relatively stable. On the other hand, the volatility is relatively active. Let's compute the summary stats for the monthly log returns. Select the cell where you'd like the summary table to be displayed. Then switch to the NumXL tab and click the Summary Stats icon. In the input time series, select the monthly returns cell range. Accept the default settings for the remaining options and then click OK. The sample stats table is now displayed. You should note that the sample average is not significantly different than 0. Now we need to compute and plot the autocorrelation and partial autocorrelation in an effort to find the proper model. Select the cell where you'd like the output table to be displayed and then click the parallelogram icon. Select the monthly returns time series as the input data. Now change your max lags to 18 for the ACF and for the PACF. Accept the default values for the remaining options and then hit OK. The parallelogram table and plot are now displayed side by side. Now let's reformat the ACF and PACF plots. The plot shows no significant autocorrelation in the data, so an ARMA model is not justified. That being said, the data does possess fat tails, and the EWMA swings widely throughout the sample time. Also, the returns time plot shows a clustering of volatility. This calls for a GARCH type plot. Now select the cell where you'd like the table to be displayed, and then click the GARCH icon. Select the monthly returns cell range as the input data. In a financial time series, the volatility reacts differently for negative returns than it does for positive returns. eGARCH captures this phenomenon, so let's go with an eGARCH model. Now click OK. The eGARCH model's parameters, its goodness of fit, and the residuals diagnosis are displayed in your worksheet. Notice that the parameter values are initial and by no means optimal. Now we can calculate the model's parameter values. To start, select the cell where the model begins. Then click the calibration icon in the toolbar. Now the Microsoft Excel solver will pop up. Notice that all the fields in our solver are already initialized with our model formula and parameter cells. Now hit Solve. The solver found a solution. The optimal parameter values are now copied into your worksheet. Notice that all of our residual diagnosis checks worked, except the ARCH test. Now let's compute the long-run conditional volatility. Type the function eGARCH_vol into the formula. Click the function wizard icon FX. The eGARCH vol depends only on the model parameters. Select the cell range for the alphas and for the betas. Notice that we use a Gaussian distribution for the innovations or shocks. This is the default, so we leave the rest blank. Now reformat. Now we can reforecast. Select the cell that describes the model, or the one that says eGARCH11. Now switch to the NumXL tab. Click on the forecast icon. The forecast dialog should appear. The model field is set to the current selected cell and is grayed out. For the input data, select the most current observations from your data set. You can leave the realized volatility blank, moving the standard deviation and volatility values from a third-party source. For our purposes here, we use the EWMA as a proxy for the monthly volatility. Select the cell range for the realized volatility. Note that for eGARCH, we need at least one realized volatility value. Now we can specify the forecast horizon. We can put 24 for a 2-year forecast. Now select the output range. We picked the cell immediately below the model table. Now click OK. The table is displayed, starting from the output cell that we selected. Now we can plot the local conditional volatility and the term structure for the next 12 months. Now reformat the graph. And that's it. If you have any questions, comments, or concerns, please send them to us at support@spiderfinancial.com.